Hey guys, welcome to another lecture, lecture number 14. So today we will talk about implicit differentiation and also about logarithmic differentiation. You will see that the situation will get a little bit more complicated with in computing derivatives, but not that much. And in fact, I already covered the chain rule, so that will be useful in some circumstances. But this will be a little bit longer than usual. Probably you didn't like the fact that the last lecture was more than 1 hour and a half, but anyway, it happens sometimes. I'll try to be as short as possible, like to keep the lectures, let's say, to be at most 1 hour and 20 minutes, 1 hour and 30 minutes, but that's no more than that. Unfortunately, the last one was 1 hour and 50 minutes. I hope it won't happen with this one, but anyway, let's not lose any time. Let's get started. Okay, so let me start with something easy so that you can get a little bit the picture of what's going on in here. So like I said in the title, we will be talking about implicit and logarithmic differentiation. Anyway, let's write it, implicit and logarithmic differentiation. Okay. Well, I decided to devote the first part, most of this lecture, to implicit differentiation, and then at the end, maybe the last 20 minutes, 30 minutes, we will talk about logarithmic differentiation. You will see what happens with when we have a function power some other function. There is a procedure of computing the derivative of this. But anyway, we'll get there. First, before I even go and talk about the implicit differentiation, let me talk about explicit differentiation. Okay, but now let me say that the function y, and you will see that this y is a function of x, but let's write it, y written explicitly and let me emphasize on this word explicitly, as a function of x, right? All right, and we say here that the variable y, right? Well, let's put is defined only in terms of x. So that's a very important thing to know. In terms of x. So keep this in mind. You will see that this will be very important when we will take derivatives of such things. For example, let me give you some examples here. For example, we can write y, so we'll define only in terms of x, as we have said previously. For example, let's say y is 2x plus 1, or another example could be y with square root of 9 minus x squared, as you can see, is defined in terms of x. Or for example, you can say y to be, let's cook up something, a polynomial of 5x cubed plus 2x squared minus 7, right? So this is an example. These are some examples of functions y in terms of x, of variable x. And now let me point out a remark. Let's just say that when we get the derivative of explicit functions, well, as you have been used by now, when we compute the derivative of explicit functions, we're going to write it with Leibniz notation. So we get just one, and I'm going to write it in this, dy over dx, right? All right, So this is the explicit differentiation. As you can see, the function is given explicitly in terms of x, and you can just compute the derivative, and that's it. Okay, now let's talk about implicit differentiation. Let's see what this is all about. And in this case, the function, let me point out that the function y is not defined only in terms of x, only in terms of x. So that's the first thing that we distinguish it in terms of, let me put it this way, in terms of x, right? And now some examples, let me give you some examples so that you can see explicitly what happened. For example, y squared plus x squared equals 1, right? Or another example could be something like, let's say 3y cubed plus 2y squared minus 5 equals 0, right? Anyway, and now we would like to see, so the question we would like to address, how do we differentiate? So in other words, how do we find the derivatives? How do we differentiate functions defined implicitly? So that is the big question we would like to address now. All right. The answer is given by the following. So we will follow this procedure for implicit differentiation. Now, suppose that an equation, so an equation defines y implicitly as a differentiable function of x. And now what we want to find, so we want to find dy over dx. So that's what we want to find. And now we would like to follow the this procedure. Step 1. Well, let me write it in red. Differentiate both sides of the equation with respect to x. And now remember that y is really a function of x. So we have to keep that in mind. Okay, for part of the curve. Okay, and use the chain rule, because this will be important. Use the chain rule Like I said, the chain rule will play an important part in implicit differentiation. So you must know the chain rule pretty well in order to implicit differentiate functions. So we use the chain rule when differentiating terms containing y. Right? Okay. And now step 2. Let's write again in red so that we can emphasize this. Solve the differential equation. Anyway, this is a little bit more pretentious, but it's not as hard as you think. The differential equation, but we will solve it algebraically. Equation. Algebraically. For dy over dx. Right? All right, so this is step 2. And now let's see some examples. So these are the 2 steps that you need to, I want you to look at them pretty well. So like I said, the main thing here is to look for the chain rule. And now let's see some examples. Now I'd like to start with example 1. We'll do a bunch of them. For example, let's implicit differentiate this equation here. Basically, this describes a circle of radius square root of 10. Well, if we want to implicit differentiate, so we will we'll keep in mind that we're differentiating with respect to x. So we have that dy over dx of y squared plus x squared equals dy over dx of 10. But dy over dx of 10 will be 0. So in other words, this will be equivalent with d over dx of y squared plus x squared. Right? Okay. And now by using, so this will be equivalent by using the sum rule with dy over dx of y squared plus dy over dx of x squared. So 0 will be equal to this, and this guy will be further equal to, and now keep in mind to this guy here. So to this guy, we will use the chain rule. So let's do that. So once we do this, once we use the chain rule for this guy, we'll have the following. So the derivative, keep in mind that y is a function of x. So we will have that this will be 2y times y prime, which will be written as dy over dx, plus the derivative of x squared with respect to x will be 2x, and this will be 0. Or if you want to rearrange this, which is equivalent with so this is equivalent to the following. So we would like to rearrange this a bit. And we can write it, as you can see, the 2 will go away. Y times, let me do it slowly, plus x equals 0, or equivalent dy, okay, let me write it in this way. Dy over dx is nothing else than negative x over y. Right? So as you can see, we separated this, and the derivative contains both x and y, as you can clearly see, right? So this is how we implicit differentiate. I want you to look at the example again. Well, it's not a big deal. And now let's see another, so this was example 1. And now let's see another, let's say, exercise 2. So I will alternate examples, exercise, and so on. Now the exercise asks us the following. For example, we can ask something like this. Find the slope of the tangent line to this circle, to the circle x squared plus y squared equals 10, right? At the point P of coordinates -1 and 3. Well, we have already implicit differentiated this equation, but now let me draw a picture first. Anyway, I hope my circle will be okay the way I will draw it, but anyway. Okay, imagine this is a circle. All right, it doesn't look like one. And let's just say we have here the point P. In fact, let me put another color. This is my point P here. Let's just say of coordinates -1 and 3, right? And what I'm interested is to find the slope of the tangent line to this point. So it goes like this. Okay. Right? So say this is 3 here. Ouch. So this guy is 3 here. This guy is -3 here. So square root of 10 is a little bit more than 3. Here we have 3. Here we have -3. Right? Okay, so that's the picture I want you to follow. And now what we know about the slope of the tangent line, we know that is the derivative at that point. So the slope of the tangent line at the point P of coordinates is nothing else than just the derivative of y with respect to x evaluated at that point P, or you can write it as dy over dx evaluated at -1 and 3. So that's what we need to compute. But we have already done this. So this guy, if we know that this guy is nothing else than just -x over y evaluated at -1, 3. And if you want, this is 1/3, and that's it. Big deal. So that's it. This is the end of the story, right? All right, let's do another exercise. Exercise 3. Now let's compute do another implicit differentiation, but a little bit more complicated than the first one. And let's just say we take, for example, x cubed y to the 5th plus 3x equals 8y cubed plus 1. All right, so we want to implicit differentiate this equation here. So let's do it. So we will have that d over dx of x cubed y to the 5th plus 3x equals d over dx of 8a cubed plus 1. And now this guy will be equivalent with, if we want to write it in this way, so now we're going to apply the sum rule for the derivative. So this will be dy dx of x cubed y to the 5th plus d over dx of 3x, which is the same as d over dx of 8a cubed plus d over dx of 1. All right. Now, if we look at this guy here, we can apply here the product rule. So we would like to apply here the product rule because we will see that I have the I have the product of two functions, but also when you look at this guy here, we would like to apply the chain rule, right? All right, let's do this. So this would be equivalent with, now by applying here the product rule, we will have that, let's write it in this way, y to the fifth d over dx of x cubed plus x cubed times d over dx of y to the fifth. And I'll have another chain rule here, but anyway, plus this guy, the derivative with respect to x of 3x will be 3. And this guy, now we're going to apply the chain rule here, right? So this would give us, if we look at this, right? So we will have that this will be 8y squared, right? So sorry, 8 times 3 times the derivative, 8, I take the times 3y squared times dy over dx plus, and now the derivative of x with respect to x of 1 is 0. So this would be equivalent. Further look at this. Again, we will use the chain rule here. Look here. So we will use the chain rule again. All right, so let's see, what do we have? So let's do it a little bit slowly so that we wouldn't make any mistakes. So this would be equal to, and now will be y to the fifth times the derivative of x cubed will be 3x squared plus x cubed times, and now we should be careful, this will be times 5y to the fourth times dy dx plus 3 equals 24y squared dy dx. And now we will look for terms that are similar with dy dx, so we can factor them out. Look at this guy here and this guy here. So now we will have the following. So this would be equivalent with the following. Let's write it in this way. Let's clean the terms. 3x squared y to the fifth plus 5x cubed y to the fourth dy over dx plus 3, right? Equals 24y squared dy over dx. And now we're going to treat them like terms, like we said, and we're going to combine them, right? So we will have the following. So this would be equivalent with, and let's combine this. Again, let me look at this guy, look here and look here. So let's combine them. So we will have that 3x squared y to the fifth plus 3 is the same as, let's write it this way, 24y squared minus 5x cubed y to the fourth times dy over dx. All right, so we write it in this way. Right? So you can divide, and this will be equivalent with dy over dx equals 3x squared y to the fifth plus 3, everything over 24y squared minus 5x cubed y to the fourth. Right? Or if you want, you can factor some things. If you want, okay, we can factor here 3. We want to do some extra algebra, but it's not necessarily necessary to do this. But this would be 3 times x squared y to the fifth plus 1, everything over. And now we can factor here y squared. So this would be 24 minus 5x cubed y squared. All right, so this is what we got. So that's it, right? This is the answer. We'll look at it. Okay, so that was an example. Now let me give you a harder one. So exercise 4. It's actually going a little bit too fast, but anyway, in the middle of the night. Now, we're going to have the following. Let me cook up something. So this would be e, let's say 2x plus 3y. So we have some exponentials here. So equals x squared. And now let me take some logs. So ln of xy cubed. All right. So we like to differentiate this. And now let's do it. So we have the following. So let's so we have d with respect to x of e to the 2x plus 3y is x squared minus ln of xy cubed. Of course, you can apply the basic rules of differentiation if you look at this, right? Well, the first one is that, well, here you know that this guy here, you know, the derivative of a, we're going to use the chain rule at this point. So this would be, will be what? Well, not just the chain rule, but this would be the derivative. So let's write it in this way. So it's e to the 2x plus 3y times the derivative with respect to x of 2x plus 3y. Right? So we can do this. And this would be equal to, so this part here is the derivative with respect to x of x squared minus the derivative with respect to x of ln of xy cubed. And this would be, and now let's be careful here a bit, it's e to the power 2x plus 3y times, and here the derivative with respect, so we can apply the sum rule. Anyway, let's write it. Of 3y, which is here the derivative of this guy is 2x minus, and now let's see the derivative with respect to x, and now you should be very, very careful here because we have the log and of the product. So we should be very, very careful. So this would be the product of the, we're going to apply the chain rule to this one. First, we apply the chain rule, and then we apply the product rule. So let me mention this here. On this guy here, right? We're going to apply the chain rule plus product rule. And the way we do this is the following. Look at this. So I have to differentiate the natural log. When I take the natural log of a function, let's say ln of x, so that would be by the chain rule is f prime of x over f of x, whatever that is inside, and then times the derivative of that. So we're gonna, and that the derivative of that is a product there. So this would be, let's be careful here. So it's gonna be 1 over, ouch, 1 over xy cubed, and here we will have okay, I'm going to write it like this, x d over dx of xy cubed. Let me put it this way. And this will be, so I'm just doing step by step so that you can see it clearly. And now let's see here inside. So here I'll have e to the 2x plus 3y times, this guy is 2 plus, and now I'll have 3 times dy over dx equals with 2x minus 1 over xy cubed. And now let's be careful here. So we're going to apply the product rule at this point. So we will have what? So we will have, let's write it clearly, d over dx of x times y cubed plus x times dy over dx. Okay, let me write it in this way. D over dx of y cubed. All right, so this will be equivalent to, so this guy is equivalent with the following. So let's write it, e to the 2x plus 3y times 2 plus 3 dy dx equals 2x minus 1 over x y cubed. And now let's be careful with some computations here. So this one will be y cubed, right? Because the derivative of x is 1 plus x times, and now we will apply again the chain rule. Let's mention this here. So to this guy here, we apply again the chain rule. And you should know this chain rule. We've discussed about it, right? I would like to go back to lecture number 12, I think. Yes, lecture number 12, I discussed it, and we provide many, many examples. So those of you who have problems with the chain rule, I would definitely suggest them to go back and look at it very, very closely. All right. So I'll have that. This is 3x times, okay, so we apply the chain rule. So we will have that dy over dx of y cubed will be x times 3y squared times dy dx. All right, finally, we have something here. Now at this point, we have something. And now we basically have to do the algebra. So let's do it. So this would be 2 times e to the 2x plus 3y plus 3 times e to the 2x plus 3y. All right, dy dx. And this would be 2x minus, and now let's do the algebra. So this would, the first one will be minus 1 over x minus minus what do we have here? Minus 3 over y dy dx. Okay. And now let's look for terms alike. For example, you see here dy dx. So we should isolate these guys. So this would be equivalent to, so let's look at this here, right? So let's be careful. So let's take these terms on the left-hand side. So I'll have 2 times e to the 2x plus 3y minus 2x plus 1 over x equals negative 3e to the 2x plus 3y minus 3 over y times dy over dx, which will be equal to, now if we separate, so it will be equivalent with dy over dx equals 2 times e to the 2x plus 3y minus 2x plus 1 over x. And everything over everything over, let's take all right, let's write it, negative 3e to the 2x plus 3. I think I'm put here, okay, this is 3 here plus 3y minus 3 over y. Okay. And now if you want to do the algebra and put everything together, like you want to do the computations and everything, and by computations, by some algebra, let's say, we get the following. So finally, we will write this in the following way, dy over dx, and this will be equal to, this will be 3, it will be okay. So y times 2x squared. So this will be 2x squared, okay. Yeah, it's 2x squared minus 2x times e to the 2x plus 3y minus 1, and everything over 3x times, let's see, y times e to the 2x plus 3y plus 1. Okay, so that's the formula we found. So this is how we compute this. Well, now I could ask you a question. For example, is this function differentiable at 0, 0? That could be a nice question. So basically, you will have to evaluate what happens to the derivative of this dy over dx at 0, 0, and you will see that you will get something. Anyway, I'm not going to insist on that. I will leave it to you as an exercise. Now let's do another one. So exercise, what number is this? Number 5. So exercise number 5, again, let's take something with some trigonometric function. For example, sine of x squared plus y equals y squared times 3x plus 1. Now solution. Now, again, we have that d over dx of sine of and as you can see here, we have a bunch of functions. Well, y is in terms of x, we have sine of it. So we would like to, we will apply the chain rule. We will apply also the product rule. So there will be a combination of these rules. And now let's see with the first one, what happens here. This guy will be nothing else than just the cosine. So we know that the derivative of sine is cosine, but it will be the cosine of x squared plus y times the derivative, so dx over dx of x squared plus y. And now let's see here again, here we apply the chain rule. Right? And here we will apply in first instance the product rule. So this guy here, if you look at it, so like I said, here we will apply the product rule. And this would give me the following. This would give me, let's say, y squared times d over dx of 3x plus 1 plus 3x plus 1 times d over dx of y squared. And this will be equivalent with, now let's, as you can see, we applied the product rule, but now we will apply the chain rule here. Well, the sum rule and the chain rule is actually simple, but anyway, let's not mention this. So this would be cosine of x squared plus y times. So d over dx of x squared will be 2x plus dy over dx. And here we will have y squared times 3 plus 3x plus 1 times, and here we'll have 2y dy over dx. This would be equivalent with, if we do the algebra here, so this would be 2x cosine of x squared plus y plus cosine of x squared plus y dy dx. And this will be equal to 3y squared plus 2y times 3x plus 1 dy over dx. And now let's look for terms alike with dy over dx. Look at this guy here, look at this guy here. So we should separate these guys. So let's see. This will be equivalent with the following. So now let's separate them. So so we'll have, let's write it in this way, 2x cosine of x squared plus y minus 3y squared. And this will be equal to 2y times 3x plus 1 minus cosine of x squared plus y dy over dx. Okay, right, so we have this. And now this will finally be equivalent to, so dy over dx will be equal to 2x let's see, it will be 2x cosine of x squared plus y minus 3y squared, everything over 2y times 3x plus 1 minus cosine of x squared plus y. Oh my. Right, so this is what we get. Right, so that's the answer. Now I could ask you a question. In fact, let's ask this question. Find the slope of the tangent line at 0, 0. And now basically the slope of the tangent line is nothing else than dy over dx evaluated at 0, 0. And if you want to plug it in, this would give us 0, this would be 0 over 1, which is 0. So the equation of the tangent line is y equals 0. So the equation, so the answer is that the equation of the tangent line is y equals 0. And that's it. Anyway, now let's see another example. This was example number, so exercise 6. Oh, it's going pretty fast. That's good. But we still have some things to cover. Let's see. Let me take something like this. So something x squared plus y squared, but this time will not be equal to a constant. Let's say it's 5x plus 4y. All right, and now we're asked the following. Find the slope of the tangent line of x equals 5. At x equals 5. So how should we think of this problem? Because you see, you don't know the y coordinate, so you only know the x coordinate. So maybe you can determine the y coordinate. So that's the thing here, right? So let's do this. But first, let's implicit differentiate this. So differentiating, we have so let's see, what do we have? So we have that d over dx of x squared plus y squared is d over dx of 5x plus 4y. And this guy will be equivalent now. It's quite clear what to do at this point. So this is, I'm going to write it directly, 2x plus 2y dy over dx equals 5 plus 4 dy over dx. And now we can isolate this. So this would be, you look for terms alike, look at this guy here and this guy here, so we can do it. So this would be implied that dy over dx is nothing else than just so it's 5 minus 2x over 2y minus 4, right? So that's this is what we get. Okay, that's great. That was easy. Wasn't hard, right? But now look at the question. We're asked to find the slope of the tangent line at x equals 5. And now we want to notice one thing. First, we need to notice the fact that dy over dx depends on x and on both x and y. Let's point out this remark. Dy over dx depends both on x and y. So the question is we will have to answer is that what is the y coordinate when x equals 5? Okay, let's find this out. So what we're going to do, look, we're going to go back to our equation here, and we're going to replace this. So look at this guy here. So we would like to see what is y when x equals 5. So we're going to plug in x equals 5 in here, as you can see, and now we're going to find y. So what is the y? If you plug it in, this will give us, so we have that. Let's see, so we plug in x equals 5 and we solve for y. So we do this. So let's write this. We plug in x equals 5 into the equation x squared plus y squared equals, what is it? 5x plus 4y. And we obtain the following. Let's see, what do we obtain? We obtain that y squared plus 25 equals 25 plus, okay, so this is easy. So we'll obtain that y times y minus 4 equals 0. So from here we'll have y equals 0 or y equals 4. So there are two tangent lines at x equals 5. So there are two tangent lines at x equals 5 for two y coordinates, or y coordinates. So tangent line, let's see, the first tangent line, let me write it like this. So the first tangent line at the point of coordinates 5, 0, right? So this will be when y equals 0, for the first case. So the slope is dy over dx with at the point 5, 0. And now you're gonna, so this would be 5 minus 10 over 0 minus 4, and this will be 5 over 4. And now we would like to do the same thing for the second tangent line. The point 5, 4. This would be y equals 4, the second one. So the slope again will be equal to dy over dx at the point 5, 4, and we're going to plug this in into the derivative, right, to this formula here. So this would be 5 minus 10, and this time will be 5 over 8 minus 4, right? So this would be negative 5 over 4. Okay, but keep in mind what we want to find. We find the slope, but yeah, we find the slope of the tangent line. Okay, that's it. Right? Okay. Now I would like to talk about say a few things about differentiation formulas. For inverse trigonometric functions, and you'll see that the chain rule applies here as well for inverse trigonometric functions. Okay, let's see this. So if u is a differentiable function, right, of x, then we have the following: d over dx of sine inverse of u. This would be 1 over square root of 1 minus u squared times du dx, right? The derivative, as you can hear, this function u is of variable x, so keep that in mind. So for the inverse cosine will be almost the same thing. Right? Now let's see for the tangent. This would be 1 over, it's just like with the derivative, usual derivative, but you'll have this extra term, du over dx. Let's see, what else do we have? So tangent inverse, secant inverse, let's say. So the secant will be what? So secant, it will be 1 over absolute value of u times the square root of u squared minus 1, okay, times du over dx, right? And now for the cosecant, this would be well, almost the same thing, so it will be with the negative here. And let's see, what else do we have? So secant, cosecant, tangent, and cotangent. This would be negative 1 over u squared plus 1 du dx. Okay, so these are the formulas. Look at them. Anyway, now let's see some examples. I would like to do some examples, and then I think I will veer towards logarithmic differentiation. And in fact, I'll give some of the derivatives and of exponential and logarithmic functions, and then I'll veer towards logarithmic differentiation. Anyway, so let's see one example. So let's see examples. Example, I don't know which number it was. This was 7. Okay. So let's see. Maybe I should take all right, let me take a nasty one. F of x is secant inverse of e to the 2x. Okay, I'm gonna take this one. So we're gonna treat this guy here inside. Look at this guy here. This will be my function u of x. Keep that in mind, right? So what we know that if you look at the secant, look at the derivative here, right? It will be, so the derivative with respect to x of secant inverse of e to the 2x equals, and now we're going to apply that formula. So it's going to be 1 over u, which is in our case e to the 2x in absolute value, times the square root of e to the 2x squared minus 1 times the d of e to the 2x over dx. And this will be further equal to, if we want to look here, so it will be 1 over absolute value of e to the 2x times the square root of e to the 4x minus 1 times e to the 2x times 2. And if you want to cancel, so it will be 2 over the square root of, because the absolute value of e to the 2x will always be the e to the 2x because that's positive. So this is going to be 2 over the square root of e to the 4x minus 1. That's it. So that's the derivative of this. So it was easy. There are also plenty of other examples in my notes, very similar, but anyway, I don't want to waste too much time since I want to talk more about, like I said, implicit differentiation. But before I go into that, let me talk about something else as well. So we'll like the following theorem. And this theorem will concern the derivatives of, so let's write it here, the derivatives of exponential and logarithmic functions. And it basically says the following. So let's consider u, a function u. Let u be a differentiable function of x. Right? And b be a positive number, right? And let's say b is not 1 because we don't want to have problems with the logarithm. Then we have the following, and I'm just going to write the formula in this way. So d over dx of b to the power u is the same as ln of b, right, times b to the u times du over dx. Okay, that's the first formula. And then the second one for the logarithm, so the derivative of log in base b of u will be equal to 1 over ln of b and that in base e times 1 over u times du over dx. So keep these two formulas in mind. Anyway, I think I've talked about the derivative of the logarithm previously, and also we talked about the chain rule. But anyway, I want you to look at this before we do any example, because at some point I would like to do an example. In fact, 2 examples. We will do one with the exponential and one with the logarithm. All right, so let's see some examples. So example number, what was number 8? Oops. Example 8. Let's take the following function. Let's say f of x is, let's say x times 2 to the 1 minus x. I would like to compute the derivative of this. So let's see. So the derivative with respect to x of this guy here, x times x times 2 to the power 1 minus x is equal to, well, we can apply the product rule here. So this would be what? This would be 2 to the power 1 minus x times d over dx of x plus x times d over, okay, So we apply the product rule here. And this will be equal to 2 to the power 1 minus x. The derivative of that guy is 1 plus x times, and now let's compute the derivative of this guy. You see, I have an exponential here. So this will be the exponential derivative. And look at the first formula. So it will be what? It will be ln of, so this would be applying the first formula. This will be x times, so this will be the derivative of exponential function with b equals 2, and instead of variable, and with the u of x equals 1 minus x. So this would be x times log of ln of 2, right? That's times 2 to the power 1 minus x, right? Times the derivative of u, which is 1 minus x with respect to x. And this will be equal to 2 to the power 1 minus x plus x ln of 2 times 2 to the power 1 minus x. And now the derivative of that guy will be nothing else than just negative 1. So this would be 2, we can factor now 2 to the power 1 minus x equals 1 minus x ln of 2. And that's it. Anyway, I think you got the gist here. All right, now let's see another example with this time I'll pick some logarithmic function. Example 9. Before we veer towards logarithmic differentiation, let me consider let me do this one. Let's say f of x will be, now let's do another product, x squared times, and now let's take some log in base, I don't know, let's say 4 of square root of x. Okay, and now we'll assume that x is positive. We want to assume that, right? So that the square root of x actually exists. Okay, so we would like to do that. So how should we do this? First of all, we apply the product rule. So we have that d of x squared log in base 4 of the square root of x. This guy will be equal to, so now we apply here the same thing. So let me mention that we apply here the product rule. And now we will have the following. We will have that this would be, let's say, log in base 4 of square root of x times the derivative with respect to x of square root of x plus, and now I will have x squared times the derivative with respect to x of log in base 4 of x. But now everything is nice, of square root of x, sorry. So everything here is nice, so this would be equivalent with let's see. So you see here I have the derivative of a logarithmic, so I want to stress this out from the beginning. So this is the derivative of a logarithmic. Right? In base b in base 4, and the function u is square root of x. Okay, and now let's do the computations here. So this would be equal to wait, this is not, this is x squared here. I'm sorry for this. It's quite late though. This is x squared here. So this would be equal to 2x times log in base 4 of square root of x plus x squared times. And now let's be careful with this. So if we look at the derivative of the product, it will be 1 over, look at this formula here. Right? Look at the formula in red. It will be 1 over ln of b. So in our case, b equals 4. And u of x is, we said that u of x is square root of x. So it will be 1 over ln of 4 times u. Okay, so it will be 1 over ln of 4 times 1 over square root of x, right? Times the derivative of the square root of x with respect to x, which will give us, let's be careful here with the computations. So this would be 2x log in base 4 of the square root of x plus x over square root of x times ln of 4 times the derivative of this guy will be 1 over 2 square root of x. And this will give us 2x log in base 4 of square root of x plus x squared over 2x ln of 4. But this guy will be 2x log in base 4 of x. So we have square root of x plus this guy will be x over 2 ln of 4. Anyway, you can get around with that log in base 4 of the radical, but anyway. Okay, now I'm veering towards the second part, which is, like I said, I want to spend maybe 20 minutes here talking about the logarithmic differentiation. And now let's see what this is all about. Let's see what is this all about. I mean, I said at the beginning that we'll have a function powered to another function, and we would like to compute the derivative of this. So when we want to do this, we would like, this is where the logarithmic differentiation will come into play. And this let me say a few words. So this process is used to handle, let me put it this way. So this is used to handle complicated, let's say, products. Right? And quotients. And also, this process is also used to handle the exponential and exponential functions. And I would like to emphasize on this more. Exponential functions where the variable appears in both the base and the exponent. So that's very important to know. Just like we previously said. So that's what we can say about logarithmic differentiation. But you know, like I said, when you have something power to power, and or I think it's better just to use logarithmic differentiation. It's pretty fast. But anyway, I will not dwell too much on the complicated products and quotients. I think you can deal with them. You can apply the product rule if you want, and then the chain rule, and then some implicit differentiation, although that would be very complicated, and I would not advise you to do so. And the same goes for quotients, so both product and quotient. So maybe you can apply the logarithmic differentiation, but that's not the purpose for the main thing that I would like to focus more is this. the exponential functions. This is what I'm interested in. So I would like to see the exponential functions. All right, and let me give you an example. I think this was example number 10. And let me consider this function, y equals 2x to the power ln of square root of x. So I would like to compute the derivative. So find dy over dx. I'd like to find this. So what we're going to do is the following. You see, we have function 2x to the power another function, which is ln of square root of x. What we'd like to do is the following. As you can see, since we have a function power another function, we can just take the natural log of this. So let's do this. So take the natural log. So by doing this, we have the following. Ln of y is ln of 2x to the power ln of square root of x. But this guy is, so we're going to apply the basic operations of the logarithm. So this would be ln of square root of x times ln of 2x, right? And now guess what? Now differentiate both terms. So by differentiating both terms of the expression, we get the following. Ln of y prime is the same as ln of square root of x times ln of 2x. All right, let me write it with the Leibniz notation as you have been used by now. So we'll have that d over dx of ln of y is the same as d of x of ln of square root of x times ln of 2x. Okay. As you can see here, I have a product on the right-hand side. So this will be equivalent. Now we just go with the usual process of implicit differentiation. So let's do that. So this would be 1 over y dy over dx. And this would be by applying, now we apply here the product rule. And we're going to get the following. Ln of 2x times d over dx of ln of square root of x plus ln of square root of x times d over dx of ln of 2x. Okay, so this will be equivalent with 1 over y dy over dx equals ln of 2x times, and now the derivative of ln of square root of x, which will be 1 over square root of x, right, times the derivative of, so d of the square root of x. Okay, let's do it step by step. Plus, this will be ln of the square root of x times 1 over 2x times dy over dx of 2x. And this will be equivalent with 1 over y dy over dx equals ln of 2x times 1 over square root of x times 1 over 2 square root of x plus ln of square root of x times 1 over 2x times 2. And this will be equivalent with, if we do, if we look at the computations, right, I think it's pretty clear at this point what's going to happen. So this would be, so let's see, this is 1 over y dy over dx equals, now let's be careful here. So this is ln of 2x over 2x plus, this guy will be ln of square root of x over x. Okay. Or if you want to do a little bit more algebra, this will be ln of 2x plus 2 ln of square root of x, everything over 2x, right? But if we want to do some basic algebra, if we want to apply the basic properties of the logarithm, this would be ln of 2x plus ln of square root of x squared. Okay, I'm going to write it like this, square root of x, everything squared, everything over 2x. And this would give us nothing else than just ln of 2x plus ln of x over everything over 2x. Or if you want, this would be ln of 2x squared, everything over 2x. All right, but wait a second, we're not done. Keep in mind this, look at where we started from. We started from this guy here, and we ended up with this guy here. So it's not the derivative of, look, I want you to look at it. So it's not quite the derivative of y yet. So we need to do something. What do we need to do? We need to multiply by y. So this, I want you to look at this, look at it, right? It's quite clear, I hope. We probably don't see from this 10, 11, but anyway. So finally, we obtain, so we will obtain the following. So we obtain that dy over dx, so which is the derivative of my function, is y times ln of 2x squared, everything over 2x. But this guy y is nothing else than, well, y of x, which is our function, our initial function. Look at it here, right? So we will have that that this will be nothing else than just 2x times to the power ln of square root of x times ln of 2x squared over x. And we're done. So that's the derivative of our function, finally. So that's a general procedure of how to compute derivative of such things. Like I said, exponential type of power to the function, power, the function to the power another function. So that's the general procedure. Okay, guys, I think I'm going to stop here for today. This summarizes everything that we have about derivatives. Next time, I'd like to talk about related rates. That will be a very important topic. And then at the end, the last lecture for this chapter, for chapter 3, will be about linearization. But anyway, I will not insist too much on the linearization of functions on the exam. So, but the next lecture will be very important. We will see some real world applications of derivatives, and all these notions that you have learned in this chapter, you'll see them, all of them, how we apply them to in the real world situations. All right, I'm going to stop here. It's already too late. Thank you very much. So I'll see you. Bye.